In order to realize the full potential of multi-layer perceptron architectures, we need one more key ingredient, a nonlinear activation function to be applied to each hidden unit following the affine transformation. Activation functions decide whether a neuron should be activated or not by calculating the weighted sum and further adding bias with it. They are differentiable operators to transform input signals to outputs, while most of them add nonlinearities. So why is an activation function required? Firstly, if we do not apply an activation function, then the output signal would be simply a simple linear regression function. Now, a linear equation is easy to solve, but they are limited in their complexities and have less power to learn complex functional mappings from data. Secondly, a neural network without activation function would simply be a linear regression model, which has limited power and does not perform good most of the times. An artificial neural network is a universal function approximator. It means that they can compute and learn any function at all. Almost any process we can think of can be represented as a functional computation in neural networks. By using a nonlinear activation function, we are able to generate nonlinear mappings from inputs to outputs. The choice of activation function in the output layer is strongly constrained by the type of problem that we are going to solve. For example, a regression problem may have a single output neuron, and the neuron may have no activation function. For binary classification problem, it may have a single output neuron and use a sigmoid activation function to output a value between 0 to 1 in order to represent the probabilities of predicting a value for the class 1. This can be turned into an integer class value by using a threshold of 0.5, and any values below the threshold will become 0, otherwise becomes 1. A multi-class classification problem may have multiple neurons in the output layer, one for each class. For example, there will be 3 neurons for the 3 class in the famous iris flower classification problem. In this case, a softmax activation function may be used to output the probabilities of the network, predicting each of the class values. Selecting the output with the highest probabilities can be used to produce an integer class value. In the following section, we will talk about some basic types of activation function used in neural networks. The most popular choice, due to both simplicities of implementation and its good performance on a variety of predictive tasks, is the rectified linear unit. ReDU provides a very simple nonlinear transformation. Given an element x, the function is defined as the maximum of their elements and 0. Informally, the ReDU function retains only positive elements and discards all negative elements by setting the corresponding activation to 0. To gain some intuition, we can plot the function. As you can see, the activation function of ReDU is piecewise linear. When the input is negative, the derivative of the ReDU function is 0. And when the input is positive, the derivative of the reduced function is 1. Please note that the reduced function is not differentiable when the input takes value precisely equal to 0. In these cases, we default to the left-hand side derivative and say that the derivative is 0 when the input is 0. We can get away with this because the input may never actually be 0. There is an old saying that if subtle boundary conditions matter, we are probably doing real mathematics, not engineering. The reason for using residue is that its derivatives are particularly well behaved. Either they vanish or they just let the argument through. This makes optimization better behaved, and it mitigated the well-documented problem of vanishing gradient that plagued previous versions of neural networks. You should also know that there are many variants to the residue function, including the parameterized residue function. This variation adds a linear term to residue, so some information still gets through, even when the argument or input is negative. The second activation I'm going to talk about is called Sigmoid Function. The Sigmoid function transforms its input, for which value lie in the domain, to output that lie on the interval between 0 to 1. For that reason, the sigmoid is often called a squashing function. It squashes any input in any range to some value in the range between 0 to 1. In the earliest neural networks, scientists were interested in modeling biological neurons which either fire or do not fire. Thus, the pioneers of this field, the inventors of the artificial neuron, focused on thresholding units. A thresholding activation takes value 0 when its input is below some threshold, and value 1 when the input is higher than the threshold. When attention shifted to gradient-based learning, the sigmoid activation function was a natural choice because it is a smooth, differentiable approximation to a thresholding unit. Sigmoids are still widely used as activation function on the output layer. When we want to interpret the output as probabilities for binary classification problems. However, the sigmoid function has mostly been replaced by the simpler and more easily trainable residue for most use in hidden layers. In recurrent neural networks, architectures will leverage sigmoid unit to control the flow of information across time. Here, we plot the sigmoid function. Please note that when the input is close to 0, the sigmoid function approaches a linear transformation. The derivative of the sigmoid function is more complicated compared to the one for residue. Note that when the input is 0, the derivative of sigmoid function reaches a maximum of 0.25. As the input diverges from 0 in either direction, the derivative approaches 0. Similar to sigmoid function, the hyperbolic tangent function also squashes its inputs, transforming them into elements on the interval between -1 to 1. We can plot the hyperbolic tangent function here. Please note that as the input nears 0, the hyperbolic tangent function approaches a linear transformation. although the shape of the function is similar to that of the sigmoid function. The hyperbolic tangent function exhibits point symmetry about the origin of the coordinate system. The derivative of hyperbolic tangent function is also similar to the one in sigmoid function. As the input nears 0, the derivative of the hyperbolic tangent function approaches a maximum of 1. And as we saw with the sigmoid function, as the input moves away from 0 in either direction, the derivative of the hyperbolic tangent function approaches 0. Before we explore the inputs and outputs of the softmax activation function, we should focus on its building block, the sigmoid or logistic activation function that works on calculating probabilities values. The output of the sigmoid function was in the range of 0 to 1, which can be thought of as probabilities. However, sigmoid function cannot deal with multi-class classification problem because the sum of all the classes' probabilities should be equal to 1. Therefore, softmax function was developed. It is a combination of multiple sigmoids, and it calculates the relative probabilities. Similar to the sigmoid activation function, the softmax function returns the probabilities of each class. It is most commonly used as an activation function for the last layer of the neural network in the case of multi-class classification. Assume that you have 3 classes, meaning that there would be 3 neurons in the output layer. Now, suppose that your output from the neurons is 1.8, 0.2, and 0. Applying that softmax function over these values to give a probabilistic view will result in the following outcome: 0.9, 0.1, and 0. The function returns 1 for the largest probability index, while we return 0 for the other 2 array indexes. Here, giving full weight to index 0 and no weight to index 1 and index 2. So, the output will be the class corresponding to the first neuron out of 3. You can see now how softmax activation function makes things easy for multi-class classification problems. To wrap up this part, an activation function is critical for a neural network to learn complex patterns in the data. There are different types of activation functions, and we need to match the activation function for output layer based on the type of prediction problem that we are solving, specifically the type of predictive variable. As a rule of thumb, ReLU activation function should be firstly used in the hidden layers by default, while sigmoid function should not be used in hidden layers, as they make the model more susceptible to problems during training. Sigmoid function should be used in the output layer for binary classification, while softmax function should be used in the output layer for multi-class classification.